So this is the title of my presentation, and the work I'm going to present has been done in collaboration with our friends Guido Boffetta, Stefano Isacchi, Laura Rozzella, and Filippo. The talk is essentially divided into two parts. In the first part, I give a very short review on what we know on radial turbulence, both in 2 dimensions and in 3 dimensions. And this serves as an introduction to the second part on the viscoelastic radial turbulence, where I describe how polymers modify the mixing properties of the classical radial problem, and in which way heat transfer is enhanced by the presence of polymers. So, a brief review on the Rayleigh-Taylor setup, as already emphasized by Guido in his talk. You can imagine to have just one fluid having different temperature in a way that the coldest part of the fluid is placed above the warmest one. Or if you think in terms of densities, this means that the denser part of the fluid is placed above the lighter one. And you, of course, you have an interface. And this flow configuration is, of course, is unstable in the sense that it is enough that you put a small perturbation to the interface, and immediately an instability grow up. This is the radial instability. Everything in this problem is controlled by the so-called atom number, defined in this way, essentially the difference, normalized difference of the two densities in the problem. And if you can easily perform linear analysis by means of classical potential theory, and you immediately obtain that the growth rate at level of linear analysis, the exponential behavior of the perturbation, is this square root of AGK. This is a classical results where K is the wave number of the perturbation imposed to the interface. Okay. So what happens in the late stage of the evolution of the perturbation? Of course, we have after the linear behavior, we have what is called a weak nonlinear regime, which is characterized by some important nonlinear interaction between thermal plumes, but sooner or later we fall in a fully developed turbulent regime, which is the focus of this presentation. Of course, here there are no polymers, as you can see. So this is a classical settings. As Guido has already emphasized, the 2-dimensional case is completely different than the 3D case. The 2D case is characterized by a scale-by-scale balance between the buoyancy term, this is buoyancy, and the radial terms. And the result of this scale-by-scale balance is the so-called Bolzano scaling, which has been argued by Cherkov by means of his phenomenological theory in 2003, and then was verified by ourselves in 2006, and more recently by Luca Mitarara and co-workers. Okay? So this is the predicted Bolzano scaling, where notice that apart the space behavior, these are the exponents, this one and this one for velocity and temperature, you also have a time dependence, which is a reminiscence of the fact that in this problem the integral scale is growing in time. Okay, so the problem is intimately unstationary. Okay, so this for what concerns the 2-dimensional case, and the dimension is completely different from the 3D case. In the 3D case, it has been again argued by Misha Cherkov that buoyancy has to be negligible at all scale apart from the largest scales, where it dominates. Okay, so the resulting system is actually a classical Navier-Stokes equation with the forcing acting concentrated on large scales here. So the phenomenology is the classical phenomenology of Kolmogorov for the velocity field, which blows towards the smallest and smallest scales, while temperature behaves according to the Kolmogorov of causing the scenario, at the reta scale of temperature fluctuations. And also in this case, we verify this kind of behavior, and the resulting scaling, as you can see, is Kolmogorov for velocity and Kolmogorov for temperature. Again, we have this temporal behavior for the same reason I mentioned for the 2-dimensional case. So this was the brief introduction to the classical radial setting. Let me pass to the viscoelastic case. Okay, For the viscoelastic case, of course, we need to model, as usual, the heft of polymers on the velocity field, and we use the standard Odroid deep model. So forget this term for a minute. In the absence of that, we have the classical, what I described before. Now we introduce polymer in a way that we can define the so-called conformation tensor, sigma, which is defined here, which is simply given by r alpha, r beta, where r is the end-to-end vector connecting the two bits. Here is the Dumble model, the simplest we can imagine. That means two bits connected by an elastic springs. Okay? So this is sigma, the so-called conformation tensor, and the equation for sigma is simply advection due to the velocity. Here is stretching and compression due to the velocity strain, of course. And this is the relaxation term to the equilibrium position. The radius of which is called here R naught. Okay? And there is, of course, in general, there is a spectrum of characteristics time. Here we use the simplest of the split, and the largest relaxation time that is called the Zimmer relaxation times, the expression which is given here. So this is the exponential decay with the classical, with the typical time tau p. Okay? So these are the equation, and of course I forgot to say that this is the back reaction. This is an additional stress tensor to the Navier-Stokes equation, which is the back reaction of polymer movement flow. So the origin of non-trivial behavior of this system is due to this back reaction. Okay? The divergence of something. Okay? Oh, so the first thing that we investigate is the first question was on what happens at the level of linear analysis. Okay? So we seeded our velocity field by polymers, and we impose this small perturbation to the interface, and we ask what about the perturbation? In which way, if any, the growth rate of the perturbation is modified by polymers. This is just to have a first clue on the effect of polymers on the evolution of relative instability. So we can. The details, of course, are boring and lengthy, so I can immediately pass to the resulting equation, which is the equation for the growth rate alpha, while omega was the growth rate in the absence of polymers. Of course, this is a third-order equation, which can be trivially resolved. The resulting solution is not particularly expressive, but nevertheless we can say something on the behavior of the growth rate as a function of the elasticity. That means as a function of what I call the Zim time for the polymers. In which way? So let me discuss two relevant asymptotics for this we can obtain from the solution of this equation. The first one is the limit tau p to 0. In this case, you recover the Newtonian case, and the expression for the growth rate is given by this expression. So the effect of the polymer, at least in this asymptotic, is simply to renormalize the viscosity. This is a trivial effect. The second asymptotic is tau p to infinite. In this case, you recover, again, the Newtonian case, but in the absence of any renormalization. Why? Simply because in this limit, tau p, if you remember the equation for this equation here, you have that when tau p goes to infinite, we don't have a sufficient strain to stretch polymers. That means that this term is not finite, but goes to 0. So we neglect this term, and we end with the classical description in the absence of polymers. So the second is the trigger limit. Why I put these two asymptotics? The reason is that from implicit differentiation on the equation, the third-order equation I mentioned before, it is possible to see that alpha as a function of tau p is monotonic. Now, because of the fact that the second asymptotic, the growth rate associated to the second asymptotic is larger than the growth rate associated with the first one, we can immediately have the result that tau p is monotonic and increasing. And so this means that the instability growth rate increases with elasticity. So this is just a first clue of a possible effect of polymer that maybe can also occur in the fully developed turbulent regime, which is our focus. Okay. So at level of linear analysis, at least in this case, we can you can see that we have a speed up of the the growth rate of the perturbation. Okay, so the question is what happens in turbulence. Oh, we have of course some arguments for that. Let me start from the 2D case for the passive case in 2 dimensions. Passive means that we assume that the polymers are passive. Okay, this is just a way to carry in a way to reproduce classical dimensional argument Kolmogorov for this case. So, 2-dimensional case, I mentioned the fact that we have the Bolzano-Hobkov scaling, so delta U goes in this way.
For well, it's not intuitively, it's unclear to me, because when you start the instability, still the velocities at the shear is very small. So there's nothing happening to the polymers. So there's just to increase the viscosity.
Yeah, this is exactly the main asymptotics I derived.
So
but you have a small effect actually.
Yeah.
You have some stretching, Of course, but
the
you're right.
The number should be larger than 1.
I mean, it's just to have a clue on what happens at the level of linear analysis. Of course, the focus is turbulence. I agree that the role of polymer in linear analysis is really a small role.
Yeah, but
essentially, it's a normalization of that.
But then if the viscosity is just growing, why speeding up? If the viscosity is growing, everything should be...
Why speeding up? Because the other could have the viscosity of polymers, which goes away.
Of course.
Yeah.
Oh, with respect to this.
With respect to that.
Okay, it's relative to
Precisely, yes.
Understood.
So here we are in 2D. This behaves as Bolzano, of course, and you can evaluate the viscous Kolmogorov scale in this way, standard dimensional consideration analysis, and you have this expression. And notice that here we have T to some positive power, by the way. That means that in 2 dimensions the viscous scale increases in time. That means that this is good for numerical simulation, simply because as time runs, you simply have you don't have to increase your resolution. And as you will see, this is opposite to what happens with respect to what happens in 3 dimensions. Okay, so this is eta, and you can evaluate in a similar way the Kolmogorov time scale in this way, and you have these results. Okay, how to use this simple dimensional prediction? But simply to evaluate the Weissenberg number. The Weissenberg number is simply, it's a measure of the importance of polymer with respect to the typical dynamical times of the flow. Okay, you define the Weissenberg number as the ratio between tau and tau eta. We have evaluated by means of a simple dimensional consideration. And you have that the result is T to some power which is negative. So this means that you have to wait, and at the end, the effect of polymer completely disappears. Okay? You can rephrase this argument in terms of the lambda scale, and you can evaluate the lambda scale by definition has the ratio between the lambda scale and the typical velocity at this scale to be equal to tau p, and you immediately obtain the behavior of the lambda scale as a function of time, and again you have something which goes to 0. So this means that if you wait a sufficiently long time, the lambda scale goes below the viscous scale. That means in 2 dimensions, polymers are expected to have no effect on the dynamics. As I anticipated, the situation is completely different in 3D. In 3D, of course, you can repeat everything I did in 2 dimensions, again at level of passive polymer. Now the difference is that the velocity obeys the Kolmogorov scaling in this way. The energy flux now is constant in time, in space, of course, along the inertial range, but it of course has a time dependence for the reason I mentioned before. You can evaluate the viscous Kolmogorov scale in this way. Notice that here the exponent is negative. And this means that in 3D, already data is much more demanding from the numerical point of view, because you need to show smaller and smaller scales as the time increases. This is the Kolmogorov time scales. Again, the same way to proceed. And at the end, also in this case, you can evaluate the Weissenberg number. And notice that now the exponent is positive in 3D. So this means that, as before, you can rephrase in terms of the lambda scale, and also the lambda scale, of course, as a positive exponent. That means that the lambda scale grows in time. Because of the time behavior of the integral scale here is simply the size of the mixing layer, which is growing according to t squared. Okay, so this is t squared. This is t to the power 1/2. This is t to the power, I don't remember, sorry. T to the power minus 1/4 is going to 0. So we have that L is well within the inertial range of scales. So we expect, at least in this case, to have a strong effect of polymer on the mixing properties, okay, in the mixing zone. So what we did is some numerical simulation in 3D, not in 2D for the reason I mentioned. And okay, this is a standard parallel pseudo-spectral code, the second order in the scheme, central scheme, with some details on the parameters on this simulation. And let me pass to some results. First of all, what about the coil stretch transition? Because the passive argument tells us that we expect to have a coil stretch transition. Okay, this is a simulation, so there is also the feedback. So this is an active problem, of course. And if you look at the inset here, you can immediately see that we have a coil stretch transition occurring t of the order of tau, where tau was the linear was given by 1 square root of a g k. This is tau, the time from the linear analysis. Okay, and we have a coil stretch transition, after which we have that the RMS, this is the polymer elongation root mean squared, behaves linearly in time. Okay, this behavior is compatible with the fact that the elastic energy behaves as t squared, which is not shown, but behaves as t squared. Why? Because R Hermes is simply the square root of the elastic. Yes?
Is it Oldroyd B or
is Oldroyd. So you don't have any constraint on the length of polymer. This is a good question for what I have to notice now. So in principle, this quantity, if you wait a sufficiently long time, and this becomes unbounded. Okay? But nevertheless, if you consider the probability density function of polymer elongation R normalized by R divided by RMS, we obtain something which doesn't depend on time, despite the fact that we don't have a cutoff L for the polymer elongation. Okay, and we have actually an intrinsic exponential cutoff emerged from the polymer elongation, as you can see here. So RMS depends on time. The probability density function rescaled by the RMS does not.
Is it passive polymers?
No, active.
So the equation comes from back reaction.
Precisely. This is a genuine effect of the back reaction.
And you looked at the Kramer's function?
I did?
The Kramer's function? And
No, we don't. Oh, this is just for one of the runs, but I mean it's the same for other runs. Maybe we wait for a long time in this case, or in another case we wait up to an elongation of the order 50 rather than 100, but it's qualitatively the same. What about the energy balance? You can define, of course, the total energy in these systems is given by the sum of the kinetic energy plus the elastic energy. This is the kinetic and this is the elastic energy, which is proportional to the trace of the conformation potential. This is the potential energy, P, which can be, this is the expression, can be obtained directly, this expression for P. And this is the energy balance in this case. Without this, we have the energy balance for the classical Rayleigh-Taylor problem in the absence of polymers. So the question now is, what happens to this balance due to the presence of polymers? What you can see here in this picture is that due to the presence of polymers, the potential energy consumption is increased in the presence of polymers. The dark line is the Newtonian case, and the red one is the behavior of P as a function of time in the presence of polymers. So as you can see, it decreases faster. Okay. So the energy consumption is increased, is larger in the present polymers, and the question is now how this increased consumption of P is spread in all these terms. And you can see that here, for instance, this is the behavior of the total energy. This is for the Newtonian case, the dark line. This is the red line is for the viscoelastic case, and you can see we have an increase of the growth rate of the kinetic for the total energy, and this is true also for the this is true also for the kinetic energy. Again, the kinetic energy grows faster in the presence of polymers. So the situation can be summarized in this three statement. That means, first of all, the speed up. We observe the speed up of the potential energy consumption. This is the first. We see an enhancement of the growth of the kinetic energy. And finally, this is not shown because I didn't have room to show this picture. We also have a reduction of the viscous dissipation. So, following these three statements, we can say that the situation is very similar to what is observed by Nittamer, Roberto Lenzi, and the group in Roma. The group in Roma, De Angelis, Casciola, Lenzi, and Piva. The situation is very similar to the isotropic and homogeneous turbulence. Okay, so we can speak of drag reduction, despite the fact that here we don't have boundaries. Oh, we can make more quantitative this definition of drag reduction in terms of a drag coefficient. How to define a drag coefficient in this case? It's quite easy because we can calculate the ratio between the variation of potential energy with respect to the kinetic energy. Okay. Okay. If you assume that the temperature, the average over horizontal planes, the average temperature profile behaves linearly with the elevation, you arrive immediately to this expression. What is the nice result? The nice result is that F is proportional to 1 divided 12 alpha, where alpha is the famous coefficient in front of the t-square behavior. Famous because many people wrote a huge number of articles to determine the dependence of this alpha by the boundary condition, by the initial conditions they mentioned. Many. There is also nature physics to give an idea. Okay, so alpha is simply related to this drag coefficient. So we can measure in a quantitative way the effect of viscoelasticity simply measuring this drag coefficient. So the result is here. This is the behavior of F as a function of T, normalized as usual by tau. And here we can see different curves. The first one is the Newtonian, and these are different values of the zinc time of the polymer. So Weissenberg is increased along this direction. So this is Newtonian, and as you can see, we have a reduction of F, and you can quantify this reduction of the order of 30% for this run. However, is around this value also for the other runs. Okay. So this is a way to quantify in a more quantitative way what we mean when we speak about drag reduction, in this case in the absence boundary, and of course what happens for the spectrum, we observe something very similar to what was observed again by Roberto, Nittamer, and co-workers in the homogeneous and isotropic turbulence. That means we have a reduction of the dissipation, the viscous dissipation, and we have an enhancement of the large-scale activity. Okay, so this situation is again quite similar to the homogeneous and isotropic problem. Some other property to the viscoelastic flow. What about the behavior of age, the mixing layer height, as a function of time? This is the Newtonian, this is the viscoelastic. Again, the growth rate is increased by the presence of polymers. That means that the mixing at large scales is increased by the presence of polymers. What happens at small scales, the situation is opposite, in the sense that this is the variance of temperature, the variance temperature for the Newtonian case and the viscoelastic case, and as you can see, the variance here is larger in the viscoelastic case with respect to the Newtonian one. That means that the mixing at small scale is reduced by the presence of polymers. So the situation is different depending on the scale you are focusing on. Reduced mixing at small scales. And this is also qualitative in agreement with these two pictures. This is the Newtonian case. This is the viscoelastic case, and you can see polymers are much more coherent and less mixed than in the case of in the absence of polymers. This is the last slide. What about the behavior of Rayleigh, Reynolds, and Nusselt numbers as a function of time? Nusselt is a measure of the heat transfer. It's a measure of the efficiency of the heat transfer transport. And of course, for the Rayleigh number as a function of time, this is trivial to say what happens, because I mentioned before that H is an increase in the presence of polymers. So this is the same for the Rayleigh number, of course, because you have H cubed. The same for the Reynolds number, because H is here, and you can see that also URMS is an increasing function of time. So Reynolds, the function of time, is an increasing function of time, and it's larger than in the case of the Newtonian case. What happened for the Nusselt number? The Nusselt number can be written in this form here, as a product between WRMS, H, and the correlation between W and T. Okay? This increases with the
measured where?
Yeah.
On the Hall bulk?
Yeah. Sorry?
The correlation measured on the Hall bulk.
On the bulk, yeah. The mixing layer, which is the fully developed turbulent region. Outside the nothing, of course. So what about the correlation? Because this increase, what about the correlation? Also the correlation increased the presence of polymers. So this probably is a nice indication of some correspondence you can have between this problem and the Rayleigh-Benard problem. Why? Because H, of course, is characteristic of a Rayleigh-Benard. The fact that H is a function of time is characteristic of a Rayleigh-Taylor. The fact that you can observe an increase of the Nusselt number due to the increase of this quantity maybe is a property that can be shared by other convective systems like Rayleigh-Benard. And the situation for what concerned some comparison with what we know in the Rayleigh-Benard convection is the following: is that we have a good agreement at level of qualitative level with the results of Versobenzi and co-workers, in the sense that they found an enhancement of the transport, of the heat transport. But on the other hand, we are in disagreement with some experiment by Interallers and Nikolenko that they found a reduction of the heat transfer for the
It was dominated by boundary layer.
The question, exactly, why? So, we have to believe probably that also in Rayleigh-Benard convection, we observe an enhancement of the heat transport due to polymers, simply because the heft is not due to boundaries, but to the bulk.
Depends whether or not the flux is dominated by the bulk or sorry, the energy dissipation. So if the energy dissipation is dominated by the boundary, you should expect a reduction. If it's dominated by the bulk, it's dominated by the bulk.
Okay. So we are in agreement in the sense that we don't have boundaries. So okay. This is the end, the conclusion. Okay, just 1 minute for the conclusion. We observe a speed up of Rayleigh-Taylor instability due to polymers, both at the linear analysis, both at level of linear analysis and also in the fully developed turbulent regime. Polymers increases in the large scale mixing because the growth rate of the mixing layer is faster in the presence of polymer, but on the other hand reduces the small scale mixing because the variance temperature is larger in the presence of polymer. There are many analogies with the drag reduction for homogeneous isotropic turbulence, and finally I emphasize the fact that we found that heat transport is enhanced by the presence of polymers. Okay? Some perspectives the extension to elastic fibers, which may have some interesting relation with technological application and also to the immiscible Newtonian fields. Thank you very much for your attention.
I have one question and a comment. So did you look at how energy dissipation changes when you have energy dissipation?
Yeah, it's reduced. It's reduced, yeah. Energy dissipation, at least in the asymptotic case, is essentially much smaller than the elastic dissipation. Everything is dominated by elasticity at the end of the evolution. I'm not sure the picture, but
because that is one of the ways we try to define drag reduction, or rather dissipation reduction for homogeneous isotropic flux. And other.
I showed that on the picture for the spectrum. The spectrum.
Yes, exactly. But And the other thing is that, so about the heat transport, do you have a comment of the paper of Dubiev? There is a good paper by Yves Dubiev on the heat transport
On the E-Tron, in which system?
in Rabindranath.
I don't remember.
But the related thing is that
What is the third?
I think he also sees heat transport enhancement. Right? I think he also sees heat transport enhancement.
We found that kind of that the lag, the maximum lag is small, have sorry, otherwise it's, you have heat enhancement.
So it depends on the length of the cutoff of the prolongation.
On the other hand, there is a problem with that paper that in the field of in a real polymer, you cannot change Weidenbach number and the maximum length independently.
Yeah.
So this is a problem
I know that.
Lunch. Mr. Lunch.
Yes, I can, but I made more questions. I mean, it generated the semi-private discussion, so I want to give the other people an opportunity to ask more questions.
Are you more hungry than me?
Yeah, but we have to resist our natural temptations. If there is no more question, I mean, it just means everybody's hungry. But okay, thank you very much.